Nova 412, The Dawn of the Solar Age. BBC WGBH co-production. WGBH TV, Boston.
Presentation of this program is made possible in major part by public television stations. Additional support is provided by unrestricted general program grants from the Corporation for Public Broadcasting and the Ford Foundation, and by grants from Exxon Corporation and the National Science Foundation.
Take technology that's been developed and so forth for other things and apply it to solving the problems that we have here on Earth, there's an engineer that wouldn't be excited doing this kind of work.
And just the huge scope of the operation of putting a system like this together in orbit is exciting. It'll be a real challenge, but it's the kind of thing that we think we do well.
Attention Venus site personnel. The 26 meters.
Do I want my life, career, and everything tied to this ball game? Is it worth that? And I guess I've come to the point, yeah, I want to be a part of OTEC. I want to, come what may, get down at tubes and smash, or sublime glory, whatever. I want to be in the ball game.
It's difficult to catch energy from the sun. Even on a bright day, the sunshine falling on a square foot of ground in an hour will only deliver as much heat as in a thimbleful of oil. That's not very much. But in New England, something very important is happening. Collecting sunshine is about to become big business. Surprisingly, it's the 2,000 small oil delivery firms around Boston that have decided not to fight, but to pioneer the solar age. They wondered if solar panels were going to cut down their business as oil prices rise. They built 20 experimental installations and discovered that although the oil consumption of a house fitted with panels drops by a third, they could make more profit from installing the panels than by delivering oil to that house for 7 years. This initiative is largely the idea of the president of the New England Fuel Dealers Association, Charles Burkhart.
We have the retail structure. We have the troops in the field in the form of servicemen and installation men. We have the salesmen to sell it. We are uniquely structured to be the prime outlet for the sale and installation of solar equipment in this area. Furthermore, of the 2.5 million oil burners we have installed at the present time, 743,000 of those systems are prime prospects for a 1 or 2 day installation of that type of equipment.
Energy costs in New England are 38% higher than the rest of the country. As costs rise elsewhere, so will the use of solar panels. It's the beginning of a major industry. In Japan, as in the United States, large demonstration projects have been built. Buildings where roofs of solar panels collect enough heat to warm them throughout the winter, and in summer drive the air conditioning. Government money is being used to prime the pump, to create a market, and so help the solar industries into existence. The Japanese government has invested heavily in developing a cheap aluminum panel that will last 20 years. The long-term testing began 6 years ago. They have done research to find a sunlight-absorbing coating that will last. And they've solved the corrosion problems that have previously plagued aluminum panels. But the main investment has been in the production engineering necessary to stamp them out very cheaply, exactly the way they stamp out refrigerator interiors now. The Japanese say they are ready to change this production line over from freezers to solar panels as soon as the demand comes. But this film is not about solar panels for domestic hot water. It asks the question, when the oil runs out, can solar energy run industry? Surely solar power would be cheap. After all, sunlight's free. But that's not so. In electricity, for example, the main cost is not the fuel. Even if fuel were supplied for nothing, electricity would only be 15 to 30% cheaper. The price is dominated by the capital invested in the power plant. All the equipment generating electricity from oil will have to be replaced within 30 years before the oil runs out. What is the scale of that problem? The chief of the solar program at the Energy Research and Development Administration is Dr. Robert Hirsch.
Okay, in the United States today, if you take a look at the energy production capacity that we have, its value is of the order of $2 trillion. 75% of what's there is dependent on oil and natural gas. If we are just simply to replace that equipment and our dependence over the course of the next 20 to 30 years with power supplies that depend on other than those fuels, then we will have to make an investment of the order of $1.5 trillion. That amounts to an investment of the order of $50 to $80 billion a year, and right now our investment rate in the United States is of the order of 10. So we're going to have a very difficult time. As a matter of fact, at the present rate, we're not going to get there from where we are today.
In the last 3 years, there have been crash programs to find if solar energy can replace oil. First in the league is the United States, followed by Japan. American spending has risen at an amazing rate to $300 million in 1977. The Japanese will spend $200 million each year until the end of the century. The sunlight falling on the Earth is enough to supply 100,000 times our total electrical needs. Will it ever be harnessed to power our planet? New research is exploring a variety of solar technologies to see if any of them can be ready when the oil age ends, to see if any will be cheap enough to displace nuclear power from the future. This is one of the solar technologies, a modern version of a very old idea. Collect the sun's heat with mirrors. Use them to focus the heat onto a boiler. Replace the heat of the coal or oil of a conventional power plant with the sun. The goal is to build this concept into a power station by 1980, one big enough to supply a town of 20,000 people. The government has given big research contracts to 4 companies. Each is to develop a different overall design and build the essential pieces for testing. One design will win the contract to build. The most advanced is Martin Marietta's at Denver, Colorado. This represents the mouth of the boiler into which the reflected heat has to go. It will be on the top of a tower. 3 of the mirrors, or heliostats, have been built in a valley. What shows the enormous scale of the final station is that the mock boiler is exactly the right distance from the mirrors, as if it was 450 feet up on its tower, a third of a mile away. It's being used to test how effectively heat can be sent across such distances.
Okay, Roy, would you give me 9 in synthetic track?
All the light the mirror collects has to be concentrated into the boiler mouth. It's the first time sunlight has ever been focused over such a distance.
Would you center your image control and transfer to fine track?
Fine track.
All right, control, at this time, would you bring up site 4?
All heliostats on target.
The mirrors perform well, but the economics are awful. Unless they can be built as cheaply as billboards, they will never be competitive with nuclear power. But billboards are made of plywood and don't have high-precision motors. The challenge is to find cheaper ways of collecting the heat. In Japan, they're building large mirror systems too. Troughs that follow the sun and focus the heat on a pipe. But all steerable systems face the same problem. Can you build them cheaply enough to be worth the energy they catch? These complicated and expensive troughs can only collect enough heat to produce about a kilowatt. So in Japan, it's exactly the same key problem. Will mass production make them cheap enough to use? An ideal system for making electricity is photocells. Sunlight falls on them, and the light is converted directly into electricity. No moving parts. It's the perfect solar machine. This is the biggest collection of photocells ever assembled. It cost $250,000. Yet it only produces enough electricity for 3 or 4 families. If photocells are to be used for power, they'll have to be 100 times cheaper. Only then will they become a major energy source. Reducing the cost is the long-term research goal. But in an effort to use them now, even at today's price, researchers at the Sandia Laboratory are looking at new ways to get more output. They're using plastic lenses to concentrate the sunlight to 50 times its usual intensity. The problem is that although the individual cells are used more effectively, they now have to be part of an expensive machine, a precise device that must accurately follow the sun. It only produces 1 kilowatt. That's not by itself enough to pay for it. But this machine doesn't only produce electricity. It produces hot water from the pipes that run behind the photocells. This experiment is to see if the simultaneous production of electricity plus hot water makes it economic for one of these to sit on the roof of a house. If this cell were to produce electricity for 30 years, it still would not have repaid the energy invested in making it. It was sliced from a perfect crystal of the purest silicon, refined at very high temperature. And yet 3/4 of the energy needed to make this crystal was wasted in sawing and polishing. Ways to avoid that are being investigated. One technique is to pull a thin crystal straight out of the molten silicon. This has already reduced the amount of silicon wasted to 1/7. When they succeed in reducing the ribbon to 1/3 of its thickness, it will be economical. Executive Vice President of the Mobile Tycho Laboratory in Boston, where they're developing the ribbon, Dr. Ed Mlowski.
Well, I think it's going to take about 3 or 4 years to really lick the basic technical problems which permit you to both evaluate and reach the technical objectives on laboratory scale. I think it's going to take about 5 years to get to the point where you can really start pilot production at a meaningfully lower cost than is currently available by other technologies, and about 7 years before you really turn the crank and you begin to see product coming out at costs which make it competitive in many applications, and perhaps by that time competitive with now conventional costs of power.
One of the Japanese ideas is to make a new kind of cell, one that can be built with a small amount of energy input. They say they only need 2% more efficiency, and it will be practical. This is the important step, forming the active layer not at red heat, but at only 700 degrees. In Britain, at this private laboratory, the breakthrough is claimed now. They begin with a very cheap substance, glass. floated in a bath of molten metal to make it exactly the correct but secret temperature. And then a mixture of chemicals is sprayed on. It's a process technologists are developing the world over. But here they've found exactly the right spray, the right temperature, the right times to make a cell that's efficient enough. 2 separate layers are needed, and then the cell is simply finished off by dipping it in a copper solution. The cadmium sulfide cells produce electricity at once. Even at this small scale, the claim is this cell is cheap enough to use now. Research Director Gordon Edge.
We sacrifice some efficiency through this process, but the efficiency is still sufficiently high to enable us to power a completely conventional transistor radio like this and keep it at full charge for a normal working day. The cost of this panel will be of the order of 10p, which is substantially less even than the cost of the batteries.
To power a home with conventional photocells would cost $40,000. With the sprayed cells, $400. If there are no problems in scaling up to mass production, and if the cells prove durable, such science fiction schemes as covering the deserts of the world with photocells begin to be possible. But whether cells are used like this or in small units on rooftops, there's a major problem. There is no cheap way of storing electricity. Batteries are much too expensive. The storage problem is crucial. It has unexpected ramifications.
If you were to put one of these contraptions on the roof of a house in Boston, knowing the weather patterns here, it's clear that in order to be 100% self-sufficient, you'd need a tremendous amount of energy storage, which might only be used quite infrequently. But to get 100% self-sufficiency, you'd need to have it. The optimum cost system would only provide a certain percentage of your electric power, perhaps 80%. Where do you get the other 20?
Well, why not buy it from the power companies, just as we do now? How would they react?
With something less than enthusiasm, I think, because they are having to provide backup capacity, wires, and what have you, to supply 100% of your needs for that 10 days a year or whenever it is when you need them. But if you get a good summer or even a good winter, they're not going to sell you any power. Now, how can they operate under those conditions?
Cheap storage for electricity is fundamental to solar energy. The Japanese are sure the answer is to use electricity to generate a fuel, hydrogen, which can be stored. Hydrogen production is a key component of their solar work. By 1999, they plan to replace their electricity grid with pipelines carrying hydrogen. At the Electrotechnical Laboratory in Tokyo, they're looking at ways to get hydrogen directly from sunlight. The arc lamp creates a temperature of 5,000 degrees. Water goes in and instantly disintegrates into hot hydrogen and oxygen. They have found a barrier which lets the hydrogen through but holds the oxygen back. It's inside here. This is the preliminary laboratory work. At full scale, the energy source will be the sun. The economics look excellent. Results suggest that this would make energy available at the same cost as today's electricity. Over the years, it's been shown in many countries that cars can be run on hydrogen. But the weight that had to be carried was enormous. Tons of cylinders for a range of a few miles. In fact, it is impractical to use compressed hydrogen gas as a car fuel. But this team went on to develop a car to run on liquid hydrogen at minus 500 degrees Fahrenheit. They succeeded in 1976. The liquid hydrogen is kept in a giant thermos bottle, giving a range of 600 miles. And the engine works more efficiently. On gasoline, it did 22 miles per gallon. Its performance on hydrogen is equivalent to 32. In a hydrogen future, cars could still be here if we want them. There is an alternative that does away completely with the need for energy storage. Where does the sun never set? In space. That's where NASA wants to go to build a power station. The first step in making the power satellite will be to build a space colony for 1,000 men. Space freighters are being developed to lift 230 tons of cargo into orbit. Every day for a year, flights will deliver the raw materials, and the men will build the power station, all 50 square miles of it. The rows of silver mirrors concentrate the light onto the dark lines of photocells. Their electricity is converted into microwaves and beamed down to Earth. 25 square miles of receivers convert the beam back into electricity. A major city would be totally supplied by one satellite. But the concept is not just an artist's impression. It is on its way to reality. Already, some of the basic ideas, such as the efficiency of the microwave beam, have been tested.
This is Venus site personnel. The 26-meter antenna will be moving in azimuth and elevation, and the transmitter will be radiating 250 kW out the antenna.
And NASA has reported the results with enthusiasm.
This is NASA's Goldstone tracking station near Barstow, California. Normally used to communicate with interplanetary spacecraft, the big 85-foot Venus dish, as it is called, is now also serving as a research tool to study the problems of beaming converted solar energy from a satellite in space back to Earth, where it can be reconverted to electricity. For the test, the 85-foot antenna represents an energy satellite. From its vantage point in space, it would collect and convert sunlight energy into electricity. A mile away, a 25-foot high set of receiver panels called the rectenna plays the role of a ground station. Made of aluminum, the more than 4,500 small rectenna elements are T-shaped and about 4 inches long. On a hillside beneath the receiver tower, a bank of 17 lights begins flickering on, reaching full intensity as the power increases. The results have been very promising as Goldstone researchers successfully collected the microwave beam and converted it to usable electricity with an efficiency of 82%.
Already the first shuttle has been built, and it will fly this year. The satellite project is controlled from the Johnson Space Center in Houston. Its director, Dr. Christopher Kraft.
I think one of the most dramatic things you would see would be at night in a clear sky in Texas, you would see 120 new satellites in the sky that would look like stars, and very big stars. I think it would be even more dramatic to those people who began to look at the Earth from some other solar system where human beings probably exist and see that ring of space solar power. It would be a direct indication of what our advancement in the state of the art was.
The satellite's electricity will cost between 3 to 10 times 1977 prices. A major cost is supporting the men in space during construction. But just how fast will the astronauts be able to work? Right now, engineers are developing the handling machinery, the artificial arms that will be used in space. On this mock-up shuttle is the real arm. The experiment with the astronaut is to find out how many remote cameras he needs, to see how fast he works if he has direct vision of the arm he is controlling. They're testing the detailed design of the construction equipment that will go on the end of the arm. There's no weight out there to support, so the beams don't need to be strong. Everything unpacked from the cargo pods will be spread out extremely thinly over extensive areas of space. They need gentle machines to handle and join the fragile, feather-like pieces together. The beams will be so delicate, they'll have to be built out there.
Those represent truss elements. Actually, they're similar to this, with about 1.5 meters across the face here, which is about like so. And this is about a 5th scale. And the material here is graphite fibers in a thermoplastic resin. They would be made up with a machine that starts with tape rolled up on reels. The tape of this material. Imagine this, the cap material here is flattened out and rolled up on a reel like movie film.
You can see that on your drawing.
And there would be 3 reels, and they're shown on the layout here. Now we roll it off the reel and simply bring it through. Similarly, we have to heat it, and those design details are to be determined, but we make long beams, let's say about 200 meters long. We join those together to form a platform.
The main problems of the satellite are not technical, they're political. The satellite has to compete with the other solar projects funded through the Energy Research and Development Administration, ERDA. Dr. Robert Hirsch.
As far as the satellite concept is concerned, that is something that, in the eyes of most people, can aptly be considered far out, pun intended. The total cost, if one just costed it to produce energy from satellites, has already been estimated to be of the order of $50 billion. And since it's early on, I'm sure that the numbers would have to be much larger. So there are many, many questions with respect to that particular concept. We're pursuing it at a relatively low level. I personally would not be comfortable in scaling up that activity until we have much, much more information than we have today.
I think when we get to the point where larger amounts of money are required, where we got to go into large experiments in space, where we really want to get around to building pilot stations, then I think the program will be turned over entirely to NASA. It will be, I think, taken out of ERDA's hands at that point, and the money's funneled directly to NASA. And that's appropriate, and I'm sure it will happen that way.
It's a possible scheme, but hidden problems may surface. Environmental damage from the microwave beams, for instance. And the investment to get the first station built is so high that once underway, the program would be hard to stop. At the other extreme from space technology, there's nature. Catch the sunlight the way the fertile areas of the Earth do, with green leaves. It is our oldest technique for using the sun. For centuries, we've caught the sunlight in fields laid out like large solar panels. We've stored the sun's energy in grass, and the grass generated power. Detailed plans have been made to produce electricity from plant material. Simply grow energy. Have a plantation of trees and harvest the young branches continuously to burn as the fuel. Calculations show that a power station big enough to meet the needs of 250,000 people could be supported by 400 square miles, about the size of Martha's Vineyard. But the research of Rebecca McDonald and Bill Wolverton, begun for a different purpose, points in a new direction.
One of these.
They make use of a weed that for years people have been trying to destroy, the water hyacinth. They don't burn these plants, they decompose them to make a natural gas, methane. After 90 days in the fermentation tank, 1 pound of hyacinths produces 6 cubic feet of methane. Hyacinths are fast-growing plants. 1 acre can produce the equivalent of 120 gallons of oil a day. The cost of that methane would be like buying gasoline at $2.70 a gallon. The plants weren't grown as an energy crop. They are simply the byproduct of an experiment on sewage treatment. As they grow, they purify the water.
You can almost watch them grow. And if we combine the value of these plants in cleaning up waste with producing an energy source like methane, then we've got something that's realistic and desirable today. Whereas if we just grow them to produce energy, they're not economical to this point. But when we take the tremendous value of these water hyacinths here, where if we put a plant in here, a conventional plant, to treat the sewage anywhere near what these plants are doing, it would cost probably $500,000 or more.
This is a NASA project. Why is the space agency interested in flowers? Because they want to use them in space for sewage treatment in the space station, recycling water and food, an important way to make the power satellite cheaper. That is, if the flowers don't take over the job of energy generation themselves. The plant is an amazing purifier. From the laboratory, poisonous waste goes by an underground drain to be treated.
Where the water comes into this system, it has cyanides, bromides, silver, chlorinated hydrocarbons, numerous organic chemicals, which most of them are toxic. And as it goes through this filtration column, we come out the other end of it, it's about 700-800 feet, with a pure water, what we consider pure water. It's amazing what this little plant can do that multi-million-dollar plants can't do.
Solar energy is also contained in the wind. The sun heats the tropics, but the poles stay cold. Cold air sinks, hot air rises. It's this that drives the weather. The energy of the wind is almost as thin as in sunlight. For instance, in a strong 20-mile-an-hour wind, mills like these only collected the equivalent of half a gallon of oil an hour. They died because energy was cheaper out of the ground. Since the Second World War, there have been many attempts to build big mills generating electricity. In all of them, the blades didn't face into the wind. The hub pointed downwind, and the blades went through the patch of dead air behind the tower. An early one on Orkney Island, North Scotland, 1950. Here it was just about to have its sails fitted. The Danes built one at Gedser, which ran till '69. The biggest was in New England, but they all failed. Their sails broke off because of metal fatigue. Now there's a new United States windmill. It too has its sails on the downwind side of the tower. NASA expertise at building aircraft wings went into designing a blade that would survive for at least 20 years. It's big, as big as a Boeing 707. But it soon ran into trouble. In a wind from an unusual direction, the blades began vibrating, and such overloadings were recorded that it seemed they might be about to fail. It was suspected that the vibrations were caused by the blades hitting a pocket of still air, a wind shadow behind the tower. At that time, there was a staircase up the center.
Okay, we're ready.
The tower did completely block the wind from one direction. They found that simply by removing the staircase, the problem would go. So after modification, the mill is in action again. Now the key technical question was, could the speed be held constant? The blades alter within 1/10 of a second to match any changes in wind strength.
Okay, let's start it up now at about 5 RPM. Okay.
The speed control has to be near perfect if, as planned, rows of such mills are to feed their power into the electricity grid.
All right, it just started to rotate. At about 5 RPM, I'll switch over to automatic. Speed's coming up.
The crucial test was to see if the control was sensitive enough to synchronize with the electricity grid.
All right, I'm going to switch controls to automatic on speed control.
And then attempt to switch the mill in.
System is on and operating.
Speed's coming up. 15. Start the computer. Computer's going. We're synced.
This mill only produces about the same power as this car's engine. It could just cope with running one elevator in the Empire State Building. The mill is only a stepping stone, a tool in the development of bigger machines. From measurements they've made here, they're going up in scale to one that will make electricity at the same price as we buy it today. The next size will draw 15 times the power. It will be very big, bigger than a 747 this time. Chief designer of the project, Ron Thomas.
Now, with those kinds of machines, and that's what we're talking, 1 to 2 megawatt machines, then you ask, well, what kind of an impact will we have on the energy and so forth? Well, it really depends on how much the need is there. If the oil becomes very scarce, as many people predict, or if the Arabs should turn off the oil, the advantage that the wind turbines have is that you can crank them out very quickly, have a wind turbine up in a year or so, and just keep bringing them off assembly lines and putting them up. All the hydroelectric systems in the United States today only produce 4% of our electric power. I firmly believe that wind turbines have the potential to easily do double that, say at 8%. Now that's a big impact.
The big mills will only be efficient in strong winds, where the average wind exceeds 18 miles an hour. The mills will be out in the Great Plains, exporting electricity to the cities. The search is on for designs that eliminate the tower. That would save a quarter of the cost of the mill and so make them economical in areas of lighter wind. This is perhaps the most promising. It has some vibration problems, but they've now been analyzed and understood. The economics of this look very attractive. A machine of this type, but 20 times bigger, is being built now. For wind energy, the future looks bright. The sun drives the wind, and the wind's energy is in turn captured by the sea and stored as waves. Quite unlike any other solar source, energy is dense here. The equivalent of 3/4 of a gallon of oil an hour is flowing toward us across each foot of sea.
Can we try the 30-knot Pearson Moscovitch, Jamie?
Yeah. 150 to 30 knots. First 4 knobs should all be at 1.
Right.
Then 4, 6, 9, 10,
4, 6, 9, right.
10, 11, 11, 12, 11, 11, 2
In
tens,
Scotland, at Edinburgh University, they have a way of converting that energy into electricity.
That's
Stephen Salter is designing the equipment that will sit in the sea. They're programming a computer to drive a wave maker so that it simulates the waves from a 30-knot wind. The waves rock a wave barrier, and that rocking motion will drive a generator. With waves, there's no storage problem.
Waves are extremely efficient at sending energy to each other. They can go hundreds of miles without losing much of their energy. In fact, we can detect waves here that have come all the way from a storm at Cape Horn. They're really remarkably efficient as energy transmitters.
The work here is to develop a shape which responds to the waves and absorbs their energy, leaving a flat calm behind. That sign of success could be easily seen when a small-scale experiment was tried on a lake. It produced the power predicted. Salter calculates that each mile of the full-scale machine will produce the equivalent of 2,000 gallons of oil an hour. It will pay back the energy needed to make it in less than a year. The full scheme would be about as long and as heavy as the highway between London and Glasgow. But it could produce all the electricity that Britain needs.
As far as the costs are concerned, it's really very difficult to put a figure on that. But we've had a go at doing sums as if we were building them today with today's costs. And it's close enough to the present day cost of electricity for us to be encouraged to go on, and also to persuade a private company to put some money into it, which is perhaps the best test.
The most spectacular possibility is to make use of the heat stored in the ocean. Cold polar water sinks and spreads over the bottom. Hot tropical water floats on the surface. The temperature difference of the tropical seas can be used to generate electricity. The concept is called Ocean Thermal Energy Conversion, OTEC. Strange machines will float in the sea generating power. They suck in warm water from the surface, and a long pipe reaches down for the cold water at the sea bed. The machinery is simple in principle. The warm surface water goes to a tank where it boils liquid ammonia. The cold water goes to a second tank where the ammonia gas is cooled back to a liquid. The liquid ammonia is pumped from the cold tank to the warm tank. It turns to high-pressure gas, which turns the turbine, making electricity. And all it needs to drive it is warm and cold water. It's been done before. In 1935, a Frenchman, Georges Claude, built one onto a ship. He took it to deep water off the tropical coast of Brazil. With the power, he planned to make ice to sell in Rio. It worked, but he lost his heavy cold water pipe again and again. It kept breaking off its buoy as it was slammed up and down in the waves. After several frustrating attempts, he ceremoniously played the Marseillaise and in disgust blew it all up. In the 1950s, he tried again off the African coast, this time attempting a shore-based turbine. The pipe was assembled beneath floating winches. Sections were joined underwater and then lowered to the seabed. The pipe proved very expensive and full of problems. It had to be 2 miles long, flexible, and not corrode. But the economics looked better than before because it had been found that pumping up rich water from the seabed caused a fantastic increase in the local population of fish. The value of the fishing would be expected to be 5 times the value of the electricity. In 1956, the scheme was finally abandoned. Today, the most advanced OTEC work is in Japan. This experiment was unknown until we were allowed to film it. The Japanese are making the critical measurements on the heat exchangers. In principle, they are simple things in which heat flows from one fluid to another. In here, the warm water inside the hollow metal tubes is warming the ammonia and making it boil. The vapor expands upwards into the turbine at the center. That turns the generator. The cost of the electricity will be critically dependent on how good the heat exchangers are. They're experimenting with a high-performance condenser, where the liquid ammonia runs down the grooves on the cold water pipe. When scaled up, it will need a surface of 150 acres. From their measurements, they have estimated the exchanger costs. They find their electricity from OTEC will be much the same price as electricity from oil. In the United States, engineers have been very frustrated because only small-scale theoretical studies have been funded. But IRDA has recently decided to dramatically increase its OTEC budget. Now there is a development program leading to the construction of a prototype by 1984. Suddenly, the engineers who have been producing the theoretical designs have to shift gear. Instead of pleading a case for it, now they're competing for the contract to build it. One of the design teams is led by Robert Douglas.
And you want to do what he wants. If you identify with the result that
This was their first meeting after the new funding was announced.
Look, fellas, the thing is, we're where we want it to be. We're poised, and from this point on, it's going to be a lot of hard work, but the program is real. They're going to build that 25 megawatt unit, and that's you guys have got to believe, and if they want that thing so bad, you can taste it from this point on. So
Douglas had anticipated this moment.
First, you have to do 2 things. You have to know what the product
In their
is,
paper
what you
studies,
want.
the team had made big savings by making their hull of concrete, not steel. But Douglas knew he would need some way of convincing IRDA that this was a reasonable decision.
It had been an issue. Critics had come out and said, well, TRW, you've got this big floating hull. First storm comes along, it's going to blow it away, destroy it. We didn't think that was right. The design, the technical design work we had done convinced us that it was doable. But I was trying to think of how can I, without just waving my arms or on my own authority, let's say, if I can say, don't believe me, here's a man who's done it, and believe him instead, you see that has an enormous weight. So I thought, well, I'll go over and see what's going on in Scotland and find out, if that's credible to me.
Douglas went to Scotland to see the way they were building oil production platforms for the North Sea. They are the same size as an OTEC. He found the kind of specialized skill he was looking for to build his hull. He could build in concrete at 1/7 the cost of building in steel.
I was bemused somewhat by the matter-of-factness of both the English and Scottish people I talked to. And I finally got to the point where I asked them, I said, well, isn't this fun? Isn't it really fun? And they said, yeah, this Alan Dart. And I said, doesn't it really give you a kick to build something like that? And he said, yeah, it does. But, I guess that diffidence, just put me off. Guy gets up every day and goes out to build a 300,000-ton ocean concrete structure. And, it's all. What I had in mind was that maybe, let's say in one of the yards in Scotland, to build a prototype there of an OTEC hull and then bring it across to the tropic sea, either in the Atlantic or the Pacific. But having gotten the first or second unit built in the UK, then maybe you could arrange a consortium to build them in production.
But while in Britain, he followed up on a chance conversation about an unusual heat exchanger that worked in seawater. It was 14 years old, yet it had never had any of the corrosion problems OTEC engineers worry about. It was the kind of technology he wanted. It was in the Thames estuary at the British Gas Methane Terminal. Tankers arrived there to discharge liquefied natural gas imported from Africa. The gas is at a very low temperature, so the exchanger heats it before it goes into the pipeline. What amazed Douglas was that it wasn't the stainless steel or titanium they had thought necessary, but aluminum. He'd found a patented technology to cut his costs in half. But it could be politically difficult to spend American research money in Britain. Douglas discussed it with Erda.
They naturally are not going to make a commitment to me at this point. It says, Douglas, if you get those English cats, on your team, we got a ball game. They're not going to do that. I'm going to have to first of all figure out how do I put together the UK people and the American people and our other team members and so on, and in such a way that it makes sense to us as a business proposition and to them. Then I got to worry about how do I convince our customer that it makes sense. So the ingredients are there. Now can you make a good stew?
Whoever wins the contract, the first will be built here. It will send the electricity ashore along a submarine cable. Later, they'll be out in the open ocean, generating synthetic fuels like hydrogen or methane to ship back.
How many will be in the sea in 2000? I'll answer it this way. A lot more than anybody thinks today. And that has happened enough times in the past. If we make it economic in the next 5 years, if we prove it's economic, then it has been shown in the past that all of the projections for how many you can build go out the window. And those guys in Scotland could go roaring off. If they can build a meter a day, if they can crank out those hulls for the North Sea like they did, they can do that and 10 times that if they have to, if the whole world got working on the ballgame.
If one did exploit the oceans so extensively as to obtain a one degree change in the temperature, the power that we would obtain would be sufficient to supply the world population with the same power consumption that we are accustomed to in the USA.
Clarence Zenner is the man who fought against government indifference for OTEC to be taken seriously. His team at Carnegie Mellon University in Pittsburgh originated the ideas on which the Japanese have built. Now he and his colleague, John Fetkovich, have a revolutionary new concept.
If we look a little more closely at what nature is doing, we can learn how to construct a more economical power plant than by using heat exchangers. In the natural hydrological cycle, warm water vapor from the ocean arises and carries with it water. We can essentially improve upon this system by forming foam at the surface of the water.
A concrete dome 600 feet high floats in the sea. Inside, there's a vacuum. There's hot surface water and cold water from the bottom. Water vapor will rush from the warm water to the cold. Above the warm water, they build a device to make foam. And 400 feet above, another to make the foam back to water. The rushing vapor carries the foam upward, creating a reservoir of water high in the air. If it works, they will have created a Niagara Falls in the middle of the sea, which could drive hydroelectric turbines. John Fetkovich.
Now, this is a laboratory model of the foam generator. At this end, we have a warm water reservoir. It's here that the foam is generated. It slowly begins to rise up this column. It goes up for a total height of over 30 feet. At the other end, we have a cold water reservoir, and it's there that the foam is condensed. Marty, are you ready? Yes. All right, switch on the vacuum. Now, we have the foam traveling up the tube. It's going slowly at this point. And when we go upstairs, we can see what's happening there.
This foam is being lifted by the rush of invisible vapor. It has been made with detergent, but they expect the natural foam of seawater will be stable enough for their machine. They want a foam that will easily collapse if they are to make their Niagara Falls in the middle of the ocean.
If we can succeed in doing this, we eliminate the enormous and very costly heat exchangers in a standard kind of ocean thermal plant, and this has the potential of reducing the cost by perhaps a factor of 2. And this would have enormous implications in the economic desirability of ocean thermal power.
Run out in 30 years. Our coal a few centuries later. Nuclear power is becoming less popular every day. But sunlight is clean and everlasting. These last few years may have been the most important in the 20th century. We may be looking at the dawn of the solar age.
Presentation of this program was made possible in major part by public television stations. Additional support was provided by unrestricted general program grants from the Corporation for Public Broadcasting and the Ford Foundation, and by grants from Exxon Corporation and the National Science Foundation.